Thank you all for coming to this very, very early session on EC2. My name is Adam Beglin, and I'm one of the lead solutions architects on the high-performance computing team here at AWS. And I'm really excited today to talk to you about a subject that I'm really passionate about, which is EC2 performance. You see, I work with customers who are doing things like computational fluid dynamics, gene sequencing, and semiconductor design on AWS today. And as you can imagine, performance is a really important subject for these types of customers. So what I want to do today is share with you some of the things that I've learned and the things that my customers do on a daily basis in order to get the best possible performance out of the platform. Now, this presentation, it's definitely built to be a deep dive on performance. And we're going to go pretty far into the nitty-gritty of how EC2 works. But along the way, I want to make sure that I'm highlighting actionable things that you can walk away with to make sure that you're getting the most out of the platform. I also want to talk a little bit about the process of choosing your EC2 instance. Because really, when it comes to getting the most performance out of EC2, making sure that you're picking the right instance is going to be just as important as all the tuning tips that I give you along the way. Now, EC2, it's a really big subject, and when you talk about EC2, you can talk about a lot of different things. You can talk about the APIs and SDKs that make managing it easier. You can talk about the different purchase options like spot or reserved or on-demand. And you even talk about the networking, direct connects, and VPC configurations that you go to when you actually go to use your instances. But today, I'm going to primarily focus on the instances themselves, how they work, the features that they have, and the options that you have when you go to launch them. For all those other topics, you can find a lot of other sessions here at reInvent that are going to go a lot deeper than I can into those other ways of managing EC2 and the other components of EC2. So let's dive in, and let's start at the basics. So what is an EC2 instance? Well, EC2 instances, at their simplest level, they're virtual machines. So they're guests that are sitting on top of a hypervisor that are sitting on top of a piece of physical hardware. And when we launched our first instance in 2006, almost 10 years ago, or more than 10 years ago at this point, we didn't give you a lot of choice. We gave you what we called the EC2 instance. We didn't really even have a name for it at the time. You didn't get to choose how many virtual CPUs it had or how much memory it had. You went to launch an instance, and this is what you got. Now, it made the process of choosing your instance a heck of a lot easier, but customers, they wanted more flexibility, and they wanted more choice. So we started iterating on the platform. And as you can see, we've been growing and adding a lot of new instances ever since. So this is a chart of all of the EC2 instances launched since that original M1. And as you can see, I kind of just ran out of space in 2017. Honestly, don't know a better way to visualize this, so if you have any ideas, I'm all ears. But not only have we been adding new instances, we've also been quietly changing how EC2 works underneath the hood. So let's take 2011 as an example. So we launched the CC2 instance in 2011, and this was actually the first time that we gave you the ability to choose the physical topology of your EC2 instances within our data center. And we released that feature called placement groups that lets you place your instances as close together as possible so that you'll get the best possible bandwidth and the lowest latency between your instances. This was also the instance that we introduced hardware-assisted virtualization, which really enables you to get the best possible performance out of your EC2 instances and lets us expose more of the physical hardware of the instance, of the physical machine, to your instance. So it's a really big change and enabled a lot of the things that I'm going to talk about here. Now, EC2, it's always growing and it's always changing, and it's largely based on your feedback as customers. And it's important to know that how we do things in the past may not be the same as how we do things in the future. This is especially the case with something like C5 that we launched recently, that I'll go into a little bit of detail about the changes that we made. So make sure that when you're going to launch an instance, or when you're choosing a new instance family, or you're looking at something that we just launched, check our documentation, read the blogs, read the FAQ, because it'll tell you what's changed in that instance and how you can expect the behavior to be differently than the EC2 instances that you might be used to. Now, I have a lot of customers who ask me, do I have to move to a new instance? Do I have to upgrade? And if you don't want to, you don't have to. I have customers, you can still launch the M1 instance on EC2 that we originally launched, all those years ago. But it's only available in the AZs that it was originally launched in, and we aren't putting new M1s in new, regions that we come out with. But not only, will you still be able to launch those instances, I suggest that customers upgrade because they get a lot of performance improvements just by moving to a new instance. It's usually as simple as stopping your instance, changing the type, and starting it back up, or updating your auto-scaling group. But these new instances and this new hardware, it's usually more power efficient. It's usually cheaper for us to operate. So what we do is we pass those savings on to you. So you may have noticed when we launched C5, it's actually cheaper than the C4 instance. And that's just one example. We do that typically with new hardware releases. So I highly suggest that you keep up on the latest instance because you'll get better performance on the platform and typically at a lower cost. So before we dive into the instances themselves, I want to just go over briefly, how we name instances and how we think about them. So here you'd see the name of an instance, the C5 extra large instance. And we break this down usually into about 3 different pieces. So that first letter that you see, that's the instance family. So this usually stands for the kind of resources an instance has or the workloads that it's best suited for. So you have C that stands for compute, R for RAM, I for IOPS, M for general purpose for some reason. But that's usually what you'll find. The next number that you see is the instance generation. And you can almost think of this like a version number of your EC2 instances. So a C5 instance is newer than a C4 instance, which is newer than a C3 instance. And the last thing that you see is the instance size. And I've heard these called t-shirt sizes, which is a pretty good way of thinking about them. So you've got small, medium, large, all the way up to 32x large, which is a massive shirt. But it's really, it's the same shirt, just in different sizes. And as you can see, you get a lot of choice and you get a lot of flexibility when you go to launch. I know that whenever you're in the console and you're trying to decide which instance from that massive list that you want to look at, it can be a little bit overwhelming. But I suggest by first starting at looking at the families that you're interested in. And to do that, try to understand or try to think about what your application is constrained by. So if you need a lot of memory, an R4 instance is probably the best place to start because it's in the memory optimized family. If you are compute bound, you'll want to go with the C class of instances. If you're actually pretty well balanced, or maybe you just don't know what kind of resources you need, starting with the general purpose, like the M or the T, usually are the best place to start. And then you can keep monitoring your instances and adjusting to a better suited family as you understand your workload a little bit better. And if you need a little bit of help, you can always check our documentation. For each EC2 instance, we list the types of workloads that we typically see customers use it for. So it's a good way to get started if you're just trying to think about it. But when you're looking at all those instances, you'll see something that's pretty unique to AWS, and that's the virtual CPU, or vCPU. Now, I have a lot of customers who are confused about what a vCPU is, and it's actually pretty simple. So on all modern instances that aren't in the T family, and those are special for reasons I'll talk about later, a vCPU is simply a hyper-threaded physical core. So hyper-threading has been around for a pretty long time. It's really good technology. It kind of lets your CPU do 2 different things at once. So let's say you have one thread that's waiting on I/O. You could still serve a web request to a customer on a different thread. But some customers, they need to know, or they're curious, what's the real core count, or what's the physical core count of that box? And for most cases, you can just take that vCPU number and divide it by 2. Now, if you do need to know how many physical cores you have, maybe you have licenses that are constrained by the number of physical cores on a box, you can always check this link that I have on this slide, and that'll give you an up-to-date list of all the instances and their core count. So let's give you a visual representation of what this looks like. So here you can see the output of a tool that I like. It's called LSTopo, LSTopo, and it shows you the physical topology of the hardware that you're using. You can run this on bare metal, you can run this on AWS, and it'll give you a very similar output. So here you can see the output of a M4 10x large instance. So this instance, you can see it has 2 sockets. That's the top and bottom things on the chart here. You can see how much memory is attached to each socket. You can see the level 1 through level 3 cache. And you can even see the CPU thread to physical core mapping. And you can see this because we're exposing that physical topology of the underlying instance, or of the underlying hardware to your instance. So your threads don't float between cores. So when you see a core or when you see a thread, that maps 1-to-1 to a CPU on the underlying hardware. So there's some applications that actually don't benefit from hyperthreading, and the context switching involved can actually slow down the performance of those applications. These are usually pretty compute-heavy applications. Think of things like financial calculations or engineering simulations, things that are just using a lot of compute power. Maybe they're just doing AVX or floating point calculations. On all systems, these applications typically disable hyperthreading. And if that's something that you're used to doing, you can do that on EC2. Now, if you don't usually disable hyperthreading, or if you don't know, you probably don't need to worry about any of this. But if you do, you can get that same effect on EC2. It's pretty easy to do on Linux. It's a little bit harder on Windows. So with the way that Linux exposes the physical infrastructure of the CPUs, it enumerates the first set of threads on each socket first, and then the second set of threads second. So that if you want to disable hyperthreading, all you need to do is disable that second set of threads. And you can do this 2 different ways, and I've listed both of those up here. So the first way essentially parses out the CPU mapping and hot offlines the second thread on each processor. This is a pretty good way of doing it. You don't need to reboot to have the changes to take effect. But I have some customers who are worried about system instability because you may be disabling processors that threads might be using. So a cleaner way of doing it, potentially, is to update grub. And what you can do is you can set the max CPUs option in grub to be half the number of virtual CPUs on the box. So you just update max CPUs equals whatever half the vCPU number is, update grub, and reboot. And when your instance comes up, hyperthreading will be effectively disabled. On Windows, it's a little bit difficult because Windows interleaves the threads instead of having the first set of A threads before the B threads. So in order to disable hyperthreading on Windows, you have to use things like CPU affinity to lock processes to specific physical cores. But at the end of the day, it'll have the same effect. So let's show you that LSTopo output on an M4 10x large again, but this time with hyperthreading turned off. Here you can see highlighted in blue, each physical CPU core only has 1 thread associated with it as compared to the 2 that you saw before. Now let's talk about the instance sizes and how these sizes work. So when we build instances, we build them in a way that makes it pretty easy to scale both horizontally and vertically. So let's take a look at the C5 instance as an example. So on the far left, you see the C5 18x large. So this is the biggest C5 instance. It has 72 virtual CPUs, and it has 144 gigabytes of RAM. Now that single C5 18x large is roughly equivalent in size to 2 of the C5 9x larges. So these are things like the number of virtual CPUs it has, the amount of memory that's available to it, even things like the network bandwidth that's available. And this keeps going down the line. As you go down each size, it roughly cuts the number of resources that you have in half. So you can scale, if your application needs twice as much power, you can go up just to the next size. Now, for things like the C5, 9 doesn't divide cleanly by 2. So we go from a C5 9x large to a C5 4x large. And you do have the same proportional number of CPUs in memory. That CPU to memory ratio stays the same as you change sizes. And the reason that we do this, or the reason that we build instances like this, is because of how we partition our instances on the physical infrastructure. So typically, when you're running the largest size instance, you're using an entire physical server. The smaller sizes, you're just running a fraction of that server, depending on what size instance you're running. Now, virtualization has historically gotten a pretty bad reputation. That's because in a lot of environments, it's used to over-allocate resources. So you have more instances or more virtual machines than you have physical infrastructure, and you're trying to balance that utilization. We use virtualization for a lot of other reasons. So one of the reasons that we use virtualization on AWS is to isolate instances from each other for data protection and also for resource partitioning. When we build instances, we build them in such a way that our goal is to provide you with a consistent experience no matter what else is happening on the hardware. So take the vCPUs as an example. With the exception of the T family, which is special again for reasons I'll talk about, when you're assigned a virtual CPU, you're the only customer using that virtual CPU, and you're not sharing it with anyone else on the hardware. Same thing applies to memory and network resources. We set up these isolations so that you'll get that consistent experience no matter which size that you pick. And the last thing that I want to talk about when it comes to choosing your instances, and I know it's cheesy to quote from your own documentation, but I really like the sentiment behind this. It's really easy on EC2 to get an application up and running. So instead of doing what I see some customers do, which is to install a synthetic load testing tool to count the number of flops or IOPS or whatever you get on the hardware, install your application and try sending it some realistic load to do some testing. So if you have a mobile application, try to simulate real users navigating your app. If you have an HPC application, run a common model that you're running, not a synthetic benchmark. If you have a database, try running some queries on it. By using a real workload, you'll actually understand how your application behaves on that hardware, and you'll be able to start measuring how the performance scales as you add more instances or as you go up in sizes of your instance. So definitely, I highly suggest using a real app to do your testing. Now let's dive a little bit deeper into the operating system. And on all systems, timekeeping is an important operation. So timekeeping or your clock source, it's used for things like processing interrupts, getting the time of day, and measuring performance. Most AMIs that you launch on EC2 will use the Zen clock source by default. And they do this because it's essentially compatible with almost all of our instance types now, with the exception of the C5. But around the Sandy Bridge processor, the TSC or time step counter was introduced. And what it means is that your timekeeping operations or the system calls that are using the clock will now be handled by a piece of physical hardware on your CPU and not the hypervisor, which are going to be much, much faster. So to kind of show you an example of this, I wrote a really simple application. And it just does a loop where it does get time of day 10,000 times, or even more than that. Now, don't get nervous. I'm not going to try to actually read every line of code. I'm not one of those presenters. But this is really just a simple application that I've seen that kind of represents some workloads that I've seen on the platform. And here you can see I ran that application, and I profiled it with STrace. I really like STrace because it actually shows you the system calls that are being made and how long they take and what percentage of the time that they take up. And here you can see when I ran this on an instance with the Zen clock source, my test took about 10 seconds. And as you can see, get time of day was up at the top where you'd expect it to. Now, the same exact server, all I did was I switched the clock source from Zen to TSC. And as you can see, it went from 10 seconds all the way down to 2 seconds. And get time of day doesn't even show up on that report anymore. Now, this is a pretty extreme example for a really simple app, but I've seen some applications have as much as a 40% performance improvement just by changing their clock source from Zen to TSC. So how do you do that? It's a pretty easy change to make on Linux. On Windows, you don't have to worry about it. It's handled automatically for you. And you can do it two ways, just like you can disabling hyperthreading. So the first is to do it while the system is running. The first command that I have listed shows the current clock source you're using. You can echo TSC to the clock source, and that'll make that change take effect. Or if you want it to happen every time you boot the instance, you can add the options that I have here into grub and do a reboot. Now, usually what you'll see the most difference from this change is for things like JVM debugging, performance tracing, or even some database operations. Anything that you expect there to be a lot of timekeeping calls or measuring of performance. And it's a really easy change to make. It's free. And as far as I've seen, there aren't any downsides to making this change. Another recent, or relatively recent change we made to the platform around the time of the C4 instances is giving you the ability to control the P and the C states of your instance. So let's first talk about C states. So C states control the power savings feature of your processor. So let's take a C4 8x large as an example, because I know it, I've been using it for a while. It's got a base clock speed of 2.9 gigahertz. But it allows you to turbo boost all the way up to 3.5 gigahertz on one or two cores. But in order to get that turbo boost, it actually needs to let other cores idle down so that the total heat output and power threshold of the processor stays balanced. Now, this is great for when you have a few cores or applications that need to have very high frequencies. But by letting cores idle down, it actually increases the latency of using those cores when you actually want to use them. So if you have applications where latency is a concern, you can actually limit how deep those cores will idle down by adjusting the max C state option in grub. The other option that you have is adjusting P state on a few of the instances. Now, P state is similar to C states in some ways, but what P state does is really define a consistent baseline that you want your cores to be at. So this is a good example. Let's say if you wanted all of the cores on your processor to operate at the same frequency all the time. Maybe you're sensitive to performance changes, or you want a consistent experience all the time. Game servers are actually a pretty good example of those. A lot of game servers operate in loops, and they need that loop to happen at the exact same frequency every time it operates. So you can set the P-state features of your processor to prevent your processor's speed from clocking up and down based on demand. Now let's talk about those T2 or the T instances and why they're special. T2 instances, they're really good general purpose instances. And they're, in some cases, the lowest cost instances available on AWS. I think the T2 Nano is about half a cent per hour. And they're great for things like websites or databases or developer environments, things where your CPU demand actually fluctuates over the lifetime of the instance. The way that T2 instances work is when you launch them, you get a baseline set of performance. And you'll always be, your instances will always be operating at least that baseline, and that baseline varies depending on the size of the instance that you're running. So the larger instance, the larger the baseline performance. But the magic of T2 is that you can earn credits for the time that your CPU is idle to let you burst above that baseline. So it lets you really get the performance that you need when you need it and not pay for it when you don't. We launched the T2 instances because we saw that most workloads don't use 100% of the CPU all the time. So the T2 instance is a really good way to get that balance, to get that performance that you need without paying for it. Now let's talk about how those credits work, because this is a subject that customers don't always understand. So you can kind of think of CPU credits in a T2 instance like a bucket. So when you boot the instance, you start with enough credits to do things like boot your operating system and handle the work that your instance was started up for. And when your application's up and running, you'll use credits every time you're using CPU. So a single credit will allow you to use 100% of one core for 1 minute. Now, when the work idles down and your instance becomes idle, you're going to start earning new credits that go to fill up that bucket. And the rate that you earn those credits is going to vary depending on the size of the instance. So the larger T2 instance you have, the more credits you're going to have that fill you up. Credits are also going to expire out of that bucket after 24 hours if they're unused. So there is a maximum number of credits that you can have per instance size. And so to understand, whether you are using those credits and how much you're using, and if you're choosing the right T2 size, you'll want to use CloudWatch to monitor a few different metrics. Here you can see two of the important metrics when it comes to CPU credit usage. The one in orange is the actual usage. So this is going to spike up as you're using credits on the platform. So it'll tell you how many you're using per minute. And the one that you see in blue is your actual CPU credit balance. So this is going to tell you how many credits you have left during your burst bucket, or in your burst bucket. Monitoring your credit balance is probably the one that you're going to hook on if you're using T2 instances in an auto-scaling configuration. Because whenever you run out of credits, your CPU usage is going to drop down to whatever your baseline is. And from a CloudWatch perspective, it's going to look the same as if your instance was idle or just using that level of throughput. So monitoring your credit balance over a fleet will tell you when you need to auto-scale or add more instances that'll have a higher credit balance. Next, I want to talk about X1 instances. So X1 instances, they're pretty exciting instances. They're really massive machines with 4 terabytes of RAM and 128 virtual CPUs. They're great for things that have a huge memory footprint or even high memory to core ratios with the X1E instances that we launched. Things like big in-memory databases, big data processing applications, even some HPC workloads are pretty well suited for these X1 family of instances. But when you have that much memory and when you have that much memory to use, making sure that you're using it effectively is a lot more important. On any system that has multiple CPU sockets, there's a concept called NUMA, or non-uniform memory access. And it allows you to access all the memory across all the sockets, as if it was just one big memory footprint. On Intel systems, there's the bus between each socket called a QPI, or a Quick Path Interconnect. And this is the bus that transfers memory from one socket to another. Now, accessing memory in a local socket that your process is running on is always going to be faster than going across that QPI to reading memory in another socket. So let's give you a visual representation of what I'm talking about here. So let's look at an R4 16x large as an example. So this is a dual socket box. It has 244 gigabytes of RAM on each socket. And between each socket are 2 different QPI links. So let's say you're an application on the left socket and you're wanting to read memory from the socket on the right. Transferring that memory will happen over that QPI. Now, while that's fast, it's measured in gigatransfers per second. It'll never be as fast as accessing memory that's local to that socket. And when you go to things like the X1, it gets a lot more complex. So the X1 is a 4-socket system. And because of this, NUMA becomes even more important. So compared to that R4 instance that I had on the previous slide, there's more memory per socket. On the X1E, there's almost 2 terabytes of RAM. Sorry, I think that's a typo. 1 terabyte of RAM on each socket. And there's only one QPI that connects all the sockets because there are 4 of them. And they need to be able to transfer memory to each other directly. So memory transfers from one socket to another are going to take longer on an X1 as compared to an R4. So what can you do about this? Well, if you've ever watched TOP on a Linux system, you may notice processes moving around from one core to another. This is the process scheduler in Linux, and Windows has one as well. And what it does is it tries to balance the load so that your processes are effectively using all of the hardware that you have available to you. Around the 3.8 series kernel, this process scheduler started to take NUMA affinity into account. So it'll try to keep processes in the same NUMA zone as the memory that they're accessing, but it'll also try to move memory around to be closer to the process. The downside of this is that this can actually slow down performance of some applications. And this is especially true if you have a large memory pool that spans multiple sockets. When this happens, the scheduler will spend more time moving processes around than if you just let it tell it to ignore the NUMA and let processes come and go where they may. So to disable this, you can do a couple of different things. The first option is to set NUMA equals off in grub. And this is a good use case if you have more memory that fits in one socket and you don't want the process scheduler to be moving memory around that could impact the performance of your application. Another option that you have is if you have many processes, maybe some that are coming and going, or you know that they use the memory footprint that fits within a single socket, you can use tools like NUMA CTL or Process Affinity in Windows to actually bind processes to a specific NUMA node or even to a specific physical core, since we're exposing that real topology to you. So that way they'll always access the memory that's local to them. Another thing to keep in mind is how much your operating system actually impacts the performance of your application. And using all systems, using a modern, not only is using a modern Linux distribution important, but also using a modern Linux kernel is really important. So to give you an example of this, I was visiting a customer, and they were testing a custom application, and it used a lot of memory, and it was doing a lot of memory allocations and deallocations. And they weren't seeing as good a performance on AWS as they were seeing on their on-premise systems. Now, this application, it was really complex, it was custom built, and benchmarking and testing it took a really long time. So I actually found an open source tool called eBusy that had a very similar behavior, and I profiled it with a Linux testing tool called Perf. And here you can see the results of eBusy on a Red Hat 6 system, which is the one that they were testing on. So I used Perf to profile it, and you can see that it was on this specific system, doing about 12,000 records per second. We don't know if that's good or not, but we do see that it's using a lot of system time as compared to a lot of user time that you'd expect from a well-behaved application. We'd also see by tracing it with Perf that there are a lot of page faults happening, 1.4 million in this application on this system. So what's going on here? What's actually happening? I used the Perf output and a tool called Flame Graphs that were created by Brendan Gregg, who's a distinguished engineer at Netflix. He actually has a talk later today if you want to learn more about this. But Flame Graphs are a really good way of understanding what your application is doing and where they're spending their time. So here you can see eBusy is the thread at the bottom. And you can see all the system calls. It's a little hard to read, but these slides will be up on SlideShare. You can see all the calls that they make. And up at the very top of the stack, it ends up in a memory advise call, which is a Zen hyper call. It's doing a lot of madvise calls that end up in a Zen hyper call. That's taking really the bulk of the time of this application. So what I did was I took this same exact application, same exact instance type, and I launched a Red Hat 7 instance. Recompiled it using Red Hat 7, excuse me, and you can see I got significantly better performance just by changing the operating system. The amount of records per second I got went from 12,000 or around 12,000 to 425,000 records per second. And as you can see, the system time decreased significantly. So it's spending all its time in user space where you'd expect a well-behaved application to be. And the number of page faults went down from 1.5 million to only 14,000. So what happened? Let's check out Flame Graphs again, and this really tells the story. So this is the exact same Flame Graph output from the exact same application, just compiled and run on a different system. And as you can see, there's a lot fewer calls and a lot less time being spent. And what this showed me is actually in the Red Hat 7, the glibc version that was being compiled with the application, being used by the application, instead of making all those madvise calls that end up in the hypervisor, they switched to a single Intel optimized call for memory management. So that really showed me for this application, for the way that it was using, changing the operating system made a huge difference. So I highly recommend that when you are moving to AWS, when you're thinking about using your applications, use as late of a version of the operating system as you can. Red Hat 6 especially has been around for a really long time and is not as optimized for the platform as Amazon Linux or even some of the new Red Hat releases. Next, let's talk a little bit about networking. So with the exception of the C5 instance, which I'll talk about a little bit later, EC2 instances by default use the Xen network driver to communicate over the network. This is called the NetFront driver. And this driver has a lot of overhead because of the split driver model that Xen uses to communicate. So let's say you're an application on the right, you need to write some packets. What you need to do is talk to the front-end driver that's built into your operating system. This front-end driver goes through the hypervisor, talks to a back-end driver that then has to write to the real device driver that then goes across the network. This is a pretty CPU-intensive process, and it limits your total throughput in packets per second that you can get because you have the hypervisor. You have the hypervisor being used for every network packet that you process. So what we did is we used a technology called SRIOV, or Single Root I/O Virtualization. We call it enhanced networking on our instances. And what enhanced networking does is it exposes the physical network device directly to the instance so that you don't have to have the hypervisor involved every time you're making a network packet. So enhanced networking, it's available really on all modern instance types. It's free to use, and it really optimizes that path so that you'll get much better performance and much better throughput on AWS when you're using the network. Now, to use enhanced networking, there are a couple of requirements. You have to make sure that you actually have the network driver for that network card installed in your operating system. And you have to tell EC2 that you have that driver installed so that it knows to expose the network card in a different way. So there's a flag that you have to flip on your AMI or on your EC2 instance to say that you want to use enhanced networking. But as you can see, the network path is much simpler when you go to enhanced networking. Because they don't have to transfer through the hypervisor, you get decreased jitter because you're talking to the network card itself. You'll get a higher rate of packets per second because you don't have that CPU involved in all the processing. So enhanced networking, it's free on all supported instances. It's enabled by default in a lot of AMIs, but especially customers who tend to bring their own or build their own AMI or use a VM import, it's something that's easily overlooked, and I highly recommend that you enable if you're doing anything that's using the network. And when it comes to network performance, we're still not done improving the network. We're constantly making new changes, and we launched a new network adapter along with the X1 instance that's been out on all the instances that have come out ever since. And that new network card, it's called ENA, or the Elastic Network Adapter. Now, it's an Amazon-built network card and an Amazon-built network driver. And it's going to keep growing with us as we start adding more features to the network. One of the cool things that ENA lets us do is that when we originally launched ENA on instances, we only supported 20 gigabits per second. But with back-end enhancements, with enhancements throughout the entire stack, we realized that we could offer 25 gigabits to all our customers who are using that 20 gigabit interface. So essentially, overnight, we flipped a switch, and now those instances, for free, got an extra 5 gigabits of network throughput without you having to reconfigure your operating system or really make any changes. So ENA, it's really the fastest network that we have available on AWS. It has other things like hardware checksums and receive-side steering that make it much better and more capable of packet processing. So I'm really excited about this network card. And while we're talking about network performance, I want to cover what network performance actually means on AWS. So when we show that an instance has 10 gigabits or 25 gigabits of network throughput, that's actually measured just one way. So these instances, they have bisectional bandwidth, which means that you can do that 10 gigabits or 25 gigabits both in and out at the same time. Now, the smaller instances that are listed as high, moderate, or low, the amount of throughput available to them is usually a function of the instance size. So that the bigger the instance, the more network throughput that you have available to you, just like I was talking about before. Now, if you actually want to know for those smaller instances how much throughput that you have available, I suggest using a tool like iPerf that can actually measure and monitor the packet per second performance of your EC2 instances. Now, when you want to get the 10 gigabits or 25 gigabits from one instance to another, you will need to do a little bit more, because instance bandwidth is limited to 10 gigabits per second for a single TCP stream. So if you have applications that need to be able to get more than that 10 gigabits or more than that throughput, you'll need to use multiple TCP streams from one instance to another. And you can use this, a TCP stream is just a IP port combination. We also made another change to the way network performance works, starting with R4 instances and going to new instances after that. We used to list the lower instances or the smaller instances as a low, moderate to high performance. But with instances starting with the R4, even the smaller instances, we're offering you the ability to get up to 10 gigabits per second of network throughput. And this works in a CPU credit, in a credit model that's very similar to the T2 credits. So while you get up to 10 gigabits, you do have a baseline level of throughput that's based on the instance size that you're using. And when you're not using network, you earn network credits to allow you to burst above that baseline up to 10 gigabits. So it's a really cool change in the platform that allows you to get higher rates of network throughput without having to size up to a larger instance that may have more resources like CPU or network that you don't actually need. We also made the change that I talked about around the amount of throughput that you can get per instance. So it used to be that you can only get that 10 gigabits or 25 gigabits if you're in a placement group together with other EC2 instances. But starting around this family, we actually offered the ability to get that full bandwidth available on the instances, even if you're doing things outside of a placement group, or even crossing availability zones. So you can actually get 25 gigabits from one instance to another in different AZs. But to do that, you do have to use those multiple TCP flows, because each flow is limited to 5 gigabits when you're not in a placement group. And the last thing that I want to talk about performance is some of our optimized instance families, or our accelerated instance families. Because these families are things that people don't always think about when it comes to getting performance out of the platform. So P3 instances are our newest generation of GPU-enabled instances. So these are really cool instances because they have the NVIDIA Volta V100-based GPU in them. That's a massive GPU that's really great for accelerated workloads or machine learning applications. There's a deep dive on these P3 instances, so I'm not going to go into a lot of detail on them. But they can offer, compared to the P2 instance that had the K80 GPUs that we launched just a year before them, you can get up to 2.5 performance improvement for HPC applications, or a 14 times performance improvement for machine learning use cases because of the way that they're designed and some of the tensor units that they have in them. So P3 is a really exciting instance. I highly suggest you check out the P3 deep dive if you want to learn more about them. And the next instance that is relatively new and it's really unique to AWS is the F1 instances. So these are FPGA instances. And I really like these instances because getting an FPGA used to be a really complicated process. We didn't have, to get one, you had to source the board from someplace. You had to source the FPGA itself from someplace else. And it was really, a painful process that usually only specialized people or specialized businesses really started using. But with the F1 instance, you can get an FPGA that's billed by the second, and you can use it for whatever applications that you need. We've seen it used for things like financial computing, genomics, accelerated search, and image processing. And definitely check out the F1 workshop and Chalk Talk that we have to learn how to develop for these F1s to actually improve the performance of your apps. And along this time, I've been alluding to the differences that we've been making with C5. And C5, it really is a massive change to the platform. We changed a lot, and we're going to talk a little bit at reInvent about some of these changes. But I want to talk about, from an instance perspective and from an operating perspective, what you need to know when you go to launch on C5. So with C5, we did change the hypervisor. So we're using a brand new, very custom KVM-based hypervisor on the C5 platform. And what this hypervisor does is it allows even more of the resources of the underlying hardware to be exposed to the instance itself. But because we're on this new hypervisor, because we're not using Xen anymore, we don't have that NetFront driver. So if you go to launch an instance on C5 that doesn't have enhanced networking for ENA enabled, you won't be able to get network access. You won't be able to do it. So make sure that you install the ENA driver and you set the flag on your AMI before you go to launch on the C5 instance. You'll also need to do something. You'll need to disable a feature called predictable network interface names. And this is enabled by default on a lot of modern operating systems. And what it does is that every time you install a network card into your Linux OS, it'll set that network card to be unique. And it'll always be the same every time you use it. So, let's say you have one card, it'll always be ETH0. You add another card, it'll always be ETH1. The problem with this is if you make an AMI on one instance, and then you go to launch it on the C5, it has a different PCI address. So it'll show up as a different network card. So it'll probably show up as ETH1 or something like that. By disabling predictable network interface names, your network interfaces will always show up as ETH0 if you only have one interface. And that'll allow you to actually communicate across the network, because that's what EC2 is expecting your first network interface to be. So there's a few things you have to do, and I have them on this slide, to actually disable predictable network interface names. We're also doing something different with EBS, and we're actually exposing EBS as an NVMe device. And this has a few changes that you'll need to be aware of as well. So the NVMe driver that's built into Linux, it's constantly improving with new kernel releases. So you'll need to make sure that you're on the latest one to get the best possible performance out of EBS and out of any time you're using an NVMe device. But you'll also need to keep in mind that NVMe devices are named differently than the traditional dev, SDA, whatever. So they'll show up as dev NVMe something. So to make sure that your AMIs will launch and work on different operating systems, make sure that you're using UUIDs or labels instead of actually the dev SD mapping in etcfs tab that you might be used to before. Another thing to keep in mind, and we don't have a lot of customers that run into this, but you can have a maximum number of 27 PCI devices attached to an EC2 instance with the C5 family today. And because EBS and network both show up as a PCI device, that means the total number of network or storage devices that you can have is 27 in total added together. You also need to make sure that because we're using ACPI to send shutdown signals to your OS, that you have the ACPI daemon installed and running on your OS. So if I haven't said it enough, using a modern kernel, it's really important on the platform. I've seen some customers get as much as a 40% performance improvement just by upgrading from Red Hat 6 to Red Hat 7. And the 2.6 kernel in CentOS 6 in Red Hat 6 was released in 2009. While it doesn't always feel like it, that was a really long time ago, especially in the cloud. And the last thing that I want to cover is EBS performance. And EBS performance is similar to network performance in a lot of ways in that it scales with the size of the instance that you have. So the larger instance that you have, the larger EBS throughput that you have. one of the cool things that we have, and I have the link here on the slide, is a chart of EBS performance that you can expect out of each instance size given enough EBS volumes. So you can see the max bandwidth you'll get to EBS and the max throughput and IOPS that you'll be able to expect out of a given instance size. And to get that, you'll often have to RAID multiple volumes together to be able to fully utilize that instance. It's also a great place to go for some new information that we have about burstable EBS performance that was introduced to the C5 instance. So you can get more detail there or attend the EBS deep dive to understand a lot more about that. So in conclusion, there's a lot of things that you can do to really optimize your EC2 experience. Make sure that you're benchmarking your real application, you're using a modern operating system, and you have enhanced networking available or enabled to get the best network performance out of the platform. And when it comes to virtualization, our goal is really to make virtualization as transparent as possible and to eliminate any inefficiencies that it may cause. Our goal is to provide you with bare metal-like performance. In a lot of ways, we're already there. So if you have any questions, there's some microphones up here, or I'll be on the stage or outside after this. But otherwise, launch an instance and start testing your apps. Thank you.